All right, howdy, welcome back to Professor Carbon. In this video, we're going to go over two arrow pushing mechanisms that have to do with some unusual epoxide rearrangements. If you're new to Professor Carbon, or if you just like the reminder, what I encourage everybody to do when viewing these videos is actually to take a minute and look at the problem, actually pause the video and spend some time working through it on your own. That's when you're actually going to engage in the deepest learning. And even though it's really helpful to have me narrate through all of the answers, you'll end up getting a better result by struggling through the problem on your own, even if it makes you feel uncomfortable, and then come back to the video for a little bit of help, and then go back and refocus on your own problem solving and build up that skill set. And so I'm going to encourage you to take a pause right now and check out these problems and try to solve them all on your own. All right, welcome back. And let's see if we can engage in some mechanistic arrow pushing activities here. So in this case, we have two rearrangements of epoxides. And the first one here is an epoxide to an allylic alcohol. And then the second one is going to be an epoxide to a ketone. And, in both cases, we have an H plus as our catalyst. And just as a reminder to folks, you can't go buy H plus in a bottle from a chemical vendor. That H plus has to come from some strong acid. And for these, one might use H2SO4, so sulfuric acid, or we might use tosic acid, which of course is p-toluene sulfonic acid. Let me just draw that out here. SO2 or SO3H. And so that's tosic acid. That I think about tosic acid as being kind of the organic chemist soluble, organic media soluble version of sulfuric acid. So it has the same kind of SO3H. We've just changed the other OH on the far side for a benzene ring, and that benzene ring is way less polar. And so it means we can dissolve tosic acid in solvents that might not appreciate sulfuric acid. Okay, the reason I write H plus on these questions is just so we don't get caught up in the details about worrying about exactly what's the nature of that acid. The important thing is it's a strong acid, and it's going to be able to generate protons in solution, and those protons are going to do what they always do, which is protonate things. And the nice thing is this is a pretty simple little fragment, and so there's really only one place to protonate, and that would be on the oxygen. So let's start by doing that. Now, these protonated epoxides typically undergo ring opening from nucleophiles at the more highly substituted position. And so, if we chose something like HCl, then as we protonate, we would generate Cl minus, and then that Cl minus might come back and do a nucleophilic ring opening, and that would be a fair reaction. But in this case, we're not really given a nucleophile, which is another reason why I've just used H plus instead of specifying what that acid is. And one of the nice attributes about sulfuric acid is the counterion is particularly non-nucleophilic. So it doesn't really like to behave as a nucleophile, and that usually lets something else happen. And in the case of epoxides, and I'm going to draw this as a resonance structure, which might make you uncomfortable, but if we think about it, we're only moving the electrons here to generate a carbocation and an allylic alcohol. And, the reason I'm using a resonance arrow here is because we can imagine these electrons coming back and going directly to the starting material. And in many ways, this resonance structure, as I have it drawn, is an exaggerated form of that protonated epoxide. But the reason I like drawing it here is with students, I usually tell them, anytime you draw a carbocation, they can do one of three things. They can always be attacked by a nucleophile. And at least in this problem, we already kind of discussed how I've deliberately left off any nucleophile that you could even possibly use. So that's not going to be it. They can rearrange, or they can lose a hydrogen beta and eliminate to an alkene. And that is going to be exactly what's going to happen in this case. And so I just need to draw in all of these beta hydrogens. And so this is going to look exactly like the dehydration of an alcohol, where this hydrogen now comes off And you can pick any of the 6 adjacent hydrogens. They all give you the same product, and they all generate H+. And because we started with an unspecified hydrogen in a vacuum, I'm okay losing H+ into a vacuum. I understand a lot of textbooks don't draw it that way, and they might instead draw that deprotonation with bisulfate. And the reason I don't like that is because bisulfate is actually a terrible base. So remember, the strongest acids have the weakest conjugate bases. And in this case, this is a pretty crummy base. So it always makes me uncomfortable to use that crummy of a base. That being said, carbocations are pretty acidic. I think in reality, because we always do chemistry on Avogadro's numbers of molecules, an adjacent molecule of the starting material would probably really be the base, or this alcohol would actually be the base. In either event, I'm comfortable not worrying about the exact details and just putting that H+ back into a vacuum. Okay, let's look at the next one down here. This one's a little bit unusual, and this one's going to be interesting because I think that there's actually 2 viable mechanisms depending on what we choose to do. 2 viable arrow pushing mechanisms, I should say. So let's start by having H+ protonate that epoxide just like it did before. And let's just imagine this resonance structure where it opens to the full carbocation. Okay, and before I said that carbocations can always be captured by a nucleophile, and we ruled that out for this problem. They can eliminate to generate an alkene, and we already did that up here, and that would generate the, allylic alcohol up above. The third thing they can do is rearrange. And so, we do have these pesky adjacent hydrogen atom, and we know that you can undergo an H atom shift. And many of you will tell me, but we're only supposed to do that if it generates a more highly substituted carbocation. And in this case, that carbocation already was tertiary. And so why on earth would we generate this other carbocation? But this is also a tri-substitute carbocation. And so let me just draw that hydrogen that did the migration in. And it's a very special carbocation. It's actually going to be the resonance structure of an oxocarbenium ion. So I'm going to use my resonance arrow there, and I'll keep that hydrogen drawn just for our clarity. And now we have that formal positive charge on oxygen, and I like to name this one because it's so special. And because the oxygen, when donating its lone pair, fully fills that octet, it turns out that this is a fairly stable and fairly important resonance structure. And now that H can fall off, again, for the same reasons above, I'm just going to draw it floating on into the vacuum, and that'll get us our ketone product here. So that's pretty cool. This could undergo a hydride shift, and that would be pretty neat. Now, if this were the mechanism, then the hydrogen that started here in our starting material would become the hydrogen in the product. And so we should be able to test for that. And maybe if we did that experiment, we could at least potentially find out it might not be the case. So I'm going to start a second mechanism, and I'm going to start that second mechanism from the same carbocation that we drew before. And in this mechanism, what we're going to do is the exact same thing that we did up above here, where we have a hydrogen come off and eliminate to make an alkene. But up above here, I drew 6 hydrogens, and I ignored this 7th hydrogen over here next to the oxygen. And instead of choosing one of the 6 that all give us the allylic alcohol up above, we're going to instead choose that 7th hydrogen. So if these electrons go there, that means that the hydrogen would come off as H+, And this would now generate this molecule. And for those of you that remember your keto-enol tautomerization, this is actually the enol form of the ketone. And I'm just going to highlight that here in red. So here's my enol form right there. Okay, so enol. And the enol can undergo the keto-enol tautomerization to get us the same ketone product. And to do that, we're going to invoke a two-step mechanism where we have this protonate, and I'm going to swing down those electrons. And that's going to generate the same oxocarbenium ion, and that will connect us directly up top to here. And so what I've really done in the second part is just have an alternate pathway to go from these two intermediates that goes through a different mechanism. Okay, and this gets to a very interesting question of, which of these is the correct mechanism? And I would say that they're both correct. Both of these are reasonable pathways based on all of the rules that we know in this class. And experimentally, we might be able to tease out exactly which pathway is the dominant pathway, but I would say that they're both reasonable. And if that makes you uncomfortable, that's okay. But in many ways, organic chemistry has multiple pathways, all of which can lead to the same product. And sometimes it's really difficult to discern which of those two pathways is the dominant pathway. So another example of this that commonly pops up is if a reaction could go via a radical mechanism or via a cationic mechanism. Often the things that stabilize a cation are similar to the things that stabilize a radical, and it makes it really difficult to figure out which one's which. And so we have to do a lot of experiments in the lab to figure that out. The important thing as a student, though, is to recognize that each of these follows all of your rules for an arrow pushing mechanism. So we had a carbocation, and it could eliminate to make an alkene, or it could rearrange via a 1,2 hydrogen shift. Both of those are things that you know. Both of them are reasonable things that could occur, and so they're both reasonable to put down on paper. And so I encourage you just to think about using all of those tools that you've learned and applying them to new situations. Okay, so that's all I have for this version of Professor Carbon. Hopefully you're enjoying these videos. A couple of things. Remember, if you're looking for more arrow pushing mechanism problems, you can tell that by the kind of explodey star on the side. It'll always say mechanisms, and there'll be a whole bunch of them up on the channel. And if you're looking for more content on a specific area, remember to check out our playlists. So the whole thing is organized and color-coded so that you can find the content that's the most helpful for you at this time. All right, take care and catch you next time.